Greetings, salutations, and nice things. We are starting calculus off with limits. And limits are kind of a new concept, but they talk about what we can expect of any algebraic expression or graphs themselves. When we talk about a limit, we're looking at a notation kind of like this. This might look a little weird. That's fair because it is new. Now it could be foreign. What this essentially says, though, is that as this value x approaches just some value a, f of x gets really close to L. In terms of a graph, this means as x gets close to a certain value, y is getting close to a very certain value as well. And we can see that on graphs with something like this. Now the questions I've got on the left here are the questions for you to think about on the next page, so you can fill in your answers there as we go along. I've just got them here on the left so that you don't have to, or I don't have to toggle back and forth between the pages. When we look at something like x approaching -2, we see a value of -2 right in there. So all along here, this is where x is -2. And we're talking about approaching -2, getting really close to -2. If we want, we could pretend there's a person on either side of -2, but dangling on this function, or running along it. There's someone running along there. There's someone coming along this way. And they're both just zooming in towards -2. The question is, what y value will they meet at? What are they kind of getting closer and closer to? This person over here, as they run along, they're going this way, they're going this way, they're going this way. They're getting really close to this y value of -1. And same thing with this other person. They're running along, they're going, and they're running towards that y value of -1 as well. It looks like as x gets closer and closer to -2, y gets closer and closer to -1. And that's worth filling in. If we want to use some nice fancy dancy notation, we can say f of x approaches -1. The actual value of f of -2 is just straight up, what is that y value equal to? And as we look at that, the y value, if we follow along the curve, it straight up is -1. So f of -2 is equal to 1. We've got two different notations happening for two different scenarios. This one says f of x gets really close to -1. When, of course, when x is -2, or gets close to -2. The other one says when x is -2, f of x is 1. And they are talking about different things. One is looking at what the value of y is, and the other one's looking at what it gets close to. And we'll see how that plays in other examples here. Take a moment, look at the other ones on here. Check out what happens as x approaches -9 and see what happens. Pause this video, try them out, resume the video, check your answers. And we're back. As x approaches -9, what value is f of x approaching? We go along here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So all along here is where x is 9. And again, we can think of some people on this curve running along the function. There's this person climbing up, bit of a struggle, but they're going for it. And there's this person just sliding down. Great times. Where are they going to meet? This person up here looks like they're sliding down, and when they hit an x value of -9, it looks like they're getting really close to a y value of -2. Similarly, this guy, is running along this curve, climbing up, struggling real hard, but getting really close to a y value of -2. They're both just getting infinitely close to that value. So we can say we are approaching -2. So f of x approaches -2, and that's specifically as x approaches -9. What is the value of f of -9? Well, now in that case, let's note that we actually have a hollow point. That means you have an infinitely small gap in the curve. It's so small that we really wouldn't be able to see it, but so that we can indicate that it's there, we do draw it significantly larger than it actually is. There is a hole there. F of x does not actually ever equal anything there, because x can't be 9. Again, because there is a hole. So at that point, f of x actually doesn't exist. This undivided. As x is 0, what's going on here? X is 0 right along this line here. We've got someone coming up this way. We've got someone coming at it this way. And they're both zooming along. Where are they going to meet? It looks like they're meeting in right here. They're approaching a y value of 4. Where are we at? F of x is approaching 4. And then f of 0, because it actually exists right there, there's no hollow point at this area. It's actually just straight up the curve. We can say f of x is also 4. Oops, that's f of 0 specifically. And these last couple are for when x is approaching 3. And once again, we can draw the people sliding along this curve. Whee! And this other person climbing up. What a hike. That's a weird arm. They're moving along. What are they approaching? This person's sliding down, sliding towards a height of 3. This one person's climbing up towards a height of 3. So we can say that f of x, the curve itself, is approaching a value of 3. But what is f of 3? Well, if we look along this dotted line there representing an x value of 3, again we have a hole here. So f of 3 is not along that curve, but there is a solid dot up top. That is what represents f of x at that value. So while we are approaching a height of 3, that's not what we end up getting for the value of the function. That is instead something way up high. Oh, that's like 7. That's that business there. We do note some things. Sometimes the limit is actually equal to the function's value. We saw that there. We saw that there. Those were cases where things just followed along. There were no jumps. There were no little holes or gaps in there to throw things off. And that's worth noting. But sometimes we have cases where the actual function's undefined. It's just something we're getting really close to. Or where the function's defined as something else, some completely different value from the limit, but the limit is just what do we think we're approaching. Just because it jumps rapidly all of a sudden here doesn't mean we weren't approaching something else before. So that's the busyness there. I believe we can try a couple more examples. Woo! So here's the notation in terms of those approaches. As x approaches 4, what does f of x get really close to? That's what this notation is asking. Take a moment, try it out, and we'll see what happens. I'm just going to take this and copy it to a next page. You might want to pause while you're trying things out and see what you get while I do so. Well, assuming you've paused and returned, welcome back. And if you haven't, come on, be better. Oops, I've ruined Christmas there. There we go. So we're going to find these 4 particular values here. First one is as we're approaching 4. So x value of 4, bam, 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 is there. That one we can see doesn't have any holes or anything. We're just following the curve right along. It has a value of 1, so we're just going to stick with it being 1. This one's equal to 1. As x approaches 10, if you're still thinking of the person running along the curve, then do so. There they are running along, and someone can run at them from the other side. But they're running in, converging on that particular point. That point's value doesn't exist. There is no f of 10 that's defined for us, but it looks like they're trying to meet there. So in that case, that's equal to 4. Again, we can't say f of 10 is equal to 4. That's not correct because of this hole. It does not exist. But the limit does. We do get really, really, really close to it. Over at negative 11, that's this x value here. Bam, 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 bam. And we want to draw some people standing on the curve. We can't. There's no curve to stand on. You want to draw someone running along here? No, they're just going to fall. Woo! Oh, I grabbed way too much. So we can't have anyone standing on anything there. We can't have a limit where no function exists at all. So this one does not exist. D for does, N for not, and E for exist. And finally, limit as x approaches negative 8. That's right along this stuff here. And that's just right along the curve itself. That has a value of 2. That sums up that first example, but now we have another graph to consider on this next page. In this one, we can consider a whole bunch of things, but let's specifically consider what happens as x approaches 2. And as we did previously, we're going to draw some people on here. Our line of negative 2, or of positive 2, is right along here. And someone could be on the curve on the right side of it. There they are, sliding down. And here's this person off to meet them at the same point. They said, hey, let's meet when x is negative, and when x is 2. Said, sure, see you there. And off they go. This person's sliding in, saying, yay, x is going to be 2. And here's this person running in, super excited. Sweet, I can't wait for x to be 2. They get there. What happens? What value does y approach as x gets to negative 2? Well, in this case, there are options. And those options come from this disjointedness of the curve. We suddenly jump from one chunk to another chunk. Because of that, we don't really have a distinct answer for what y approaches. On one side, it's approaching a value of negative 4. On the other side, it's approaching a value of positive 4. In the middle, we have an actual value of the function, but let's remember that the value of the function is not necessarily the same as the limit. So in this particular case, we can't say what y approaches. There's too many options. It jumps. One important thing about limits is that you have to be approaching the same thing from the left side and the right side. It's like saying to someone, oh, I'll meet you on Harrow Street, and then you both get there, but you're on completely different blocks because you didn't really establish two-dimensional coordinates, silly goofs. So if the left and right side don't match up, limit doesn't exist. We can talk about the left and right limits. This particular notation here has this tiny little negative. And what that negative says is that we are approaching 2 from the left side of it. We're looking at values lower than 2 and getting closer. Maybe 1, 1.5, 1.8, 1.9, 1.99, 1.999, 1.9999999. So on the left side, way up here, we've got this guy. That person's running in from the left, getting to an x value of 2. And that person thinks that they're hitting a value of -4. So the left limit is -4. This little plus means that we're approaching from the right side. We're going from something higher than 2, maybe 3, but we can get closer. Talk about 2.5, maybe 2.1, maybe 2.01, 2.001, 2.000000001. Infinitely close to 2, but from the right-hand side. And that's what this other character is doing up here. They're sliding in from the right-hand side of 2. And they think that they're getting really close to a value of +4. If we were to evaluate the limit as x goes to 2 for this g of x, we'd want to look at the left limit and the right limit and ensure they're the same. If they're the same, yeah, it's that value. But these are different. And because they are different, this limit does not exist. Quick. Give this one a try. Take a moment, see if you can fill in all of these. The first ones are kind of per our standard. The numbers 4 to 9 look at left limit, right limit, and ask for some business of convergence there. Again, you can pause the video, give them a try first, and then resume the video once you've given them a try. Good job on pausing. Here we go. When x approaches -6, 1, 2, 3, 4, 5, 6, looks like this curve just goes right along. Neato. Y is approaching a value of -2. We can fill that straight in. When x approaches -1, well, the left side seems to be coming in here to a value of 0. Right side seems to be coming in here to a value of 0. So that's a 0. -4 is an interesting one. We notice we have this dotted line, which we know represents an asymptote in this case. The left side seems to be approaching something that goes higher and higher. It's just rocketing right off. Where's it rocketing right off to? Positive infinity. And the right side also going way up. So they're doing the same thing. They are both going off to infinity. So that's what this limit is. I can do a slightly better infinity. That'll work. Example 4 here, or number 4, going to an x value of 4, but from the right side. So here's where x is 4. This is the right side of it. So someone's on this curve on the right side of 4 and walking towards it. That person is getting closer and closer to a y value of 1. 4 from the left side, on the other hand, might be different because, again, here's 4, here's left of 4, and there's someone on that curve left of 4. walking on in. And they're getting closer and closer to a y value of -4. Oops. This is a non-directional limit for number 6. Just what is the limit as x goes to 4? Well, we've looked at the left limit, or the left limit. We've looked at the right limit, and we've established that they are not the same. Because they are not the same, this limit does not exist. Looking at what happens when x goes to 2 from the right. Let's get rid of some stuff we don't need here. Here's our value of x equals 2. When we referenced this with the other asymptote. But maybe a person's approaching 2 from the right side. And the y value they're going towards is, whoa, they're going to go off screen to -infinity. There's that. And someone approaching from the left side is also going to be sliding down here. Maybe hanging on to this for dear life. They're sliding down. And they're also going to be going way down to -infinity as well. So what's the limit as x goes to 2? No directionality attached, not from the left, not from the right, just what is it doing, straight up. We look again at the left limit and the right limit, and we know that they are both approaching the same thing. Because they are approaching the same thing, we can say that this limit is equal to that very thing. Hence, that limit is -infinity. Quick. Try these egg samples. Now, there was a bit of a typo here in whatever notes were printed. I don't know who made this mistake, but shame on them. I will have words with them. Unfortunately, we've got -5 from the left, -5 from the left, and then -5 from the left again. Whoops, that is my bad. We'll keep all these ones the same in this column. Everything in this column, please change to being a right approach. So number 2 should be -5 from the right. Number 5 should be -11 from the right. Number 8, we're approaching 3 from the right. And number 11, we're approaching 5 from the right. Those should all be pluses. And then all these ones that are multiples of 3, we should have no directionality attached. My apologies for that. So for each one, we're going to look at the left limit, the right limit, and then straight up the actual limit. Again, give it a try, see what you get, and then resume this video. Oh, hey there! Welcome back. Hope you answered lots of questions. Let's check out what we've got. I probably won't be drawing in all the people that exist on this curve anymore, but see if you're good anyways. And of course, don't forget to ask questions via Teams or in person, whatever you need to do. Approaching -5 from the left side, that's this side of -5. We're getting closer and closer to a value of 5. Approaching 5 from the right side, that's over here. And we're getting closer and closer to a y value of 0. So then what is the actual limit as x approaches -5? We can pretty much see it graphically, but also in our answers, one of those is 5, the other side is 0. The two sides are not meeting at the same place. This limit does not exist. Going to -11 from the left, well, here's -11. On the left of it is nothing. There's nothing here. So if someone stands there, well, they'll try, and then they'll fall to their doom. It's very sad. Oh, and they left their legs behind. That's also too sad, too bad. The left limit does not exist. You can't approach it from the left. There's no curve on the left. This one does not exist. The right one does. We can approach negative 11 from the right. That's our person over on this side, zooming in towards it. They can do that. They can start wherever, like here, and go towards negative 11. And they will be approaching a value. They are approaching a value of 1. And we can fill that right in. For the non-directional one, for the two-sided limit, if you will, we look at what we got for each side. Approaching from the right, we had 1. Approaching from the left, it doesn't exist. The left and right are not the same. Therefore, this limit does not exist. Let's approach a value of 3. Here's 3, somewhere along that. And there's the curve itself. We can run along it this way. We can run along it this way. From the left, that's this one, we are honing in on a y value of 3. From the right, we are honing in on a y value of 3. So that's 3, and that's 3. For the limit as x approaches 3 overall, for this function, we note that the left limit and the right limit are giving us the same value. Therefore, the limit we get is that value. The limit is 3. And last example, we're approaching 5 from the left, then from the right. Here is our value of 5. Approaching it from the left is over here. We're approaching a value of 5. We're getting closer and closer to that point. And not actually hitting it, but getting closer. On the right side, we're coming in this way. We're moving in, and someone going along this path would be getting closer and closer to a y value of negative 2. Whoop. And it's negative 2. So to find the whole limit overall, what is the limit as x goes to 5? Again, we check. What is the left side doing? What's the right side doing? Are they the same? Hard pass. 5 is not the same as negative 2. Therefore, this doesn't equal anything. This just does not exist. And that's just kind of our introduction to limits. Again, if you have questions, comments, concerns, please make sure you reach out to me on Teams or in person in class. Let me know if you need to review the video. That's coolio. Otherwise, good luck with the practice work, and I'll see you in the future. Goodbye.